Is Dr. David Nassim from Bukhara State University, who will speak about unique KenKen over a set of complex numbers. Since David is semi-local, it was ambiguous whether he deserves a dinner or not. So since I have to do something with my wife, I decided to postpone the dinner in his honor and combine him with a speaker next semester. So everybody who comes here is still invited to come next semester.
Thank you, and thank you for inviting me, and thanks to everyone for coming today. I'm going to talk to you guys a little bit about KenKen puzzles. So KenKen is an example of a Latin square puzzle. Probably the most famous Latin square puzzle is Sudoku, where the goal is to basically find the Latin square with the elements of some set. Now Sudoku has its own extra constraint, but in KenKen puzzles what we have is we have heavily outlined regions called cages. And each of these cages has a clue, and the clue consists of both a target and an operation. And when you apply the operation to everything in that heavily outlined region or cage, you have to arrive at the target. So here's what a KenKen puzzle might look like. These are in the New York Times. They're very popular these days. So this is a puzzle with a set 1, 2, 3, 4, 5. You might look at this cage here. So what this is saying is that with the operation of subtraction, we have to arrive at the number 4. And of course, there's only one way to do that. That's with a 1 and with a 5. And this is saying with the operation of addition, I need to arrive at 3. And there's only one way to do that in this set, and that's with a 1 and a 2. And of course, that's the only way I can place the 1 or 2 when I know there has to be a 1 in one of these two cells. Similarly, I know that the remaining entries here, the 3 and 4 over here, well, there's only one way to place the two 3s so that it doesn't violate the Latin square condition. And then I could go down here to the 5, that's either a 1 and a 3, but because of the two 3s here, I can't have a 3 in either of those. So that leaves that as the only possibility. Now, this is not the puzzle that I want to talk about, so I'm going to move on and just talk a little bit about the words I was using. So a cell is what I'm going to use for a single entry, and a cage is those heavily outlined regions. An N cage is going to be a cage with N cells. So I'm going to be talking a lot about the two cages, the basic cages with two cells. The clue is going to be the target with the operation. The puzzle is the whole thing. And a Latin square is a solution if it meets all of those constraints. So I also want to talk to you guys a little bit about Brian Hayes. He's a popularizer of computer science and mathematics. He wrote for Scientific American and American Scientist. He has a few books, including a book called Group Theory in the Bedroom. And he maintains a blog called Bit Player, where he basically takes accessible problems in computer science and math and tries to get people excited about them. And one of them was called KenKen Friendly Numbers. And these are collections of numbers so that the operation is fixed. Basically, the operation is automatic once you know what the target is. That is, given the underlying set, there's only one possibility for the operation in each of the cages. Now, I'm not interested in talking about that at all today, though it's a nice article. I was interested in this side note where he said, venturing a little farther afield, we might try a 4x4 puzzle with the candidates 1, -1, I, and -I. And then he went on to say, I'm not at all sure the solution is unique or that it can be found by a purely deductive process. At best, this is a Joe KenKen. So I got interested in this because of that. This was the puzzle that was given. You can see he's got I, -I, 1, and -1. This is what it looked like. And this is a solution, so you can tell by the fact that I'm giving you the solution 5 minutes in that this is not the point of my talk. But there's a whole bunch of questions that immediately come up. So he said he didn't know whether there was a deductive process for finding this solution. And he also didn't know whether it was unique. So we could ask, is there a deductive process? What does that mean? Do we just have to look brute force, or is there some way without breaking it up? And is the solution unique? And what about those clues? What if you change the clues to other numbers from that set? Would the solution be unique? Is it possible to have no solutions? Is it possible to have more than one solution? And then that cage pattern looked kind of arbitrary there, right? Maybe if you chose a different cage pattern, there would be no solution, or there would be infinitely, well, not infinitely many, but there would be multiple solutions. And you guys could see from the puzzle that we had like sort of a nice Cayley table structure there in that solution when I showed you. So maybe that diagonal structure had something to do with making that puzzle particularly nice. And then finally, where does the structure of the complex numbers come in? So I want to answer all of these questions. So some immediate observations is it's going to be, there's definitely going to be some puzzles that have no solutions at all. And this is easy, it's just a size argument. There's 4,096 possible assignment of the clues, and there's just not enough solutions to go around. So there's going to be some puzzles with no solutions. And now, for the structure of the complex numbers, I'm going to answer this question by removing the one thing that made this puzzle interesting to some of you, probably, which is, well, all the clues were multiplication, so this was just a cyclic group of order 4. So basically,
so you can only use these. You can only use any complex numbers.
Well, he used those 4 complex numbers under multiplication. So I'm just going to map this over, because he used a cyclic group of order 4. I mean, we could come up with all sorts of complex number problems, and I make problems myself over the quaternion group, but his puzzle was just basically a puzzle over a cyclic group of order 4. So I'm just going to map this over to Z4. I have 2 choices. I've got to map generators to generators. I'm going to pick the first of these 2 choices. I'm going to map I to 1, and I'm going to make these into some doku over the group Z4. So this is the converted puzzle, and this is the converted solution. And I'm going to call this a sum doku, where I'm not going to bother writing in the operations anymore because they're all going to be plus, all going to be addition. So some things that we can say is what we can do is we can look at the 2 cages, because that's sort of the simplest thing. And a 2 cage with a clue C, well, we can count the number of solutions. It's going to be the order of the group we're working in. But we have to subtract 1 for each of the possible roots of the clue. And this is clear, because x, y equals c is going to have exactly n solutions in our group. So anytime we have x times x equals c, we lose exactly 1 solution. So this is going to enable us to count the number of possibilities for a 2 cage. Now, if our clue is 0, we're going to end up with...
Could you go back one
Yes.
slide? I'm sorry, I missed that last bit there. So your group is multiplicative or additive?
So our group is going to be additive, but this is a statement over any finite group. So I wrote this as x times y equals c.
Yeah.
So since I'm going to be moving from group to group as the talk goes on, unless I'm specifically talking about Z4, I'm going to be using just product or dots or juxtaposition.
But to non-commutative group also. What are you saying?
Yes, we can do this sort of, well, we'll talk about other groups more in a little bit. Yes, absolutely. But you're absolutely right. Here, the product is going to be addition over Z4, so the squares are actually doubles. Right? So x plus x happens to be equal to 2 if x is odd, and 0 if x is even. So we lose 2 solutions in the 0 case, and we lose 2 solutions if the clue is 2. Now, if the clue happens to be odd, we're going to still have a full 4 solutions. So I'm going to call this the 2-cage lemma. And basically, it gives us a quick way of determining what the entries are in the case that we have a 2-cage with an even clue. Okay, we're also going to have a switch trick, which allows us to replace any even and odd with the same parity counterpart. So, I mean, if I have an odd number, I'm going to use D to refer to odds in this talk, instead of O, so I don't mix it up with 0. And I have E for the evens. And of course, I can always add 4 because I'm in Z4, so I can change this odd number with its other odd number, and I can change this even number to the other even number without changing what the sum is. So whenever I have an odd and an even, I'm allowed to switch them. So I'm going to refer to this as my switch trick. Now for the multiple solutions question, I'm going to answer this in maybe one of the more roundabout ways, but if a solvable puzzle has equal and even center clues, then it's going to have exactly 8 solutions. So I'm just going to use the things that we've done so far, those 2 last lemmas, in order to show this.
And you're always going to be working with that diagram,
well, I'm going to
set
be,
of blocks.
this is actually going to be the only diagram, and I'm going to show that in a moment. But yes, for right now, we're just assuming that seemingly arbitrary diagram is the one that we're just sitting with. But there's actually something very special about that diagram. We're going to see that in a moment.
What does center mean for an arbitrary diagram?
Okay, so right now these 4 center clues. Okay, so if I have even and equal center clues, let's say here I have 0 and 0, and here I have 2 and 2, we can use the 2-cage lemma in order to determine what these are. So these would have to be odd and these would have to be even. Now because of the Latin square condition, that only leaves one way to place the remaining odds or evens. So what I end up with is a parity map for the entire board. Okay, now once I have a parity map, I look over here, I know that this odd can't be the same as this odd, and this even can't be the same as this even. Now I can't just switch these two with the switch trick, but if I switch the whole row, then I won't be violating the Latin square condition because the row contains each of the entries exactly once. So I can switch the top and the bottom rows, the left and the right columns, or I could just use the switch trick on the center. Well, not the switch trick, but I know each of the odds appears exactly once here. So I can switch the 4 center entries, and this guarantees me at least 8 solutions. And the same is true in the even case. But I also know that I'm guaranteed to have at most 8 solutions, because the board's determined by these 3 entries, and there's 2 choices for each of them. So this even will determine these 4, this even will determine these 4, this odd will determine the center, and once I know what these evens are, there's only going to be one possibility for that odd. So this shows me that there's going to be no more than 8 solutions. So if it's solvable, then it has exactly 8 solutions. And what we basically did is we broke the board down into a parity graph. From this entry and this entry and this entry, well, these two allowed us to get that, so we had one vertex in each of these cycles, and these cycles covered the entire board. So this is a trick we're going to move on to, we're going to return to later. But I want to talk a little bit about the cage pattern. That cage pattern that he chose seemed kind of arbitrary. So was there anything special or important about shaping the cages in that fashion?
But you only talk about 4 by 4 right now.
Right now.
And 1 minus 1 I minus I.
Right. So we're only talking about 4 by 4 and a cyclic group of order 4, Z4, right now. Okay. It turns out that we need to have some of the cages to have odd size. Otherwise, we can't have a unique solution. And, well, we could add 2 to each of the entries and just create a new solution. That wouldn't change the sums because it would change each of the sums by a multiple of 4. So I know that I need some cage sizes to be odd. I want to ban 1-cell cages because that's sort of like a giveaway clue, and I want to be able to put a clue in each of the cages. And I'm going to keep the vertical and horizontal symmetry that he had. So that gives me 5 possible cage patterns.
So
now,
you're not allowing, when you're trying to decide if 2 things are the same or not, you're not allowing rotations. You're not. What's the group of symmetries?
Okay, so 1 second. I'm going to consider these 2 to be isomorphic as puzzles. Because if I can solve the puzzle like this, I can just turn it like this and still solve it. It'll have the same number of solutions. I can map solutions to solutions. So these 2 I'm going to consider as actually the same. Now these 2 I'm also going to consider the same. Because I could take the 2 rows on the bottom and just switch them like this, and I can immediately map solutions to solutions. These puzzles will have the same number of solutions, and we have an easy way of going back and forth. Now, of course, I can get to this by switching the first 2 columns or by rotating from here. But this is the only one that seems different. Because this one clearly has 5 places for clues, and the others have 6 places for clues. Okay, but in Z4, we know that 0 plus 1 plus 2 plus 3 adds to 2. So I know that the top half of the board has to add to 0. So if I want to consider all puzzles, that's one thing. But if I want to consider puzzles where it's possible to have a solution, then I can automatically convert a puzzle like this by drawing a line right here. And I can set this clue by looking at what these 2 clues are, because there's only going to be one possibility that will allow the top half to add to 0. Similarly, I could go between this and this by drawing a line here and seeing what this entry needs to be. So there really is only one puzzle. So this is my 1 cage pattern. And I'm going to stick with this cage pattern for the rest of the talk. And I could draw the line here, I could draw the line here, and I could figure out what these clues need to be, or I can consider those clues. But I'm going to refer to this as P, A, B, C, D, where I'm going to go clockwise around the board. So this is my one cage pattern. Now, using the fact that the top half has to add to 0 and the bottom half has to add to 0 and the left half and the right half as well, I get these equations, but I don't even need to look at those in order to know that if I know what A is and I know what the top clues are, I immediately know what B is, and then from the right clues I get C, and then from the bottom clues I get D. So if I know what the entry of any of the 4 center cells happens to be, then I immediately get the entire center. So I'm going to call this dependence of center, and I'm going to be using that as well. Okay, so now that we have a new cage pattern, we know in order for a puzzle to have a chance at a solution, we can sort of ignore those center clues. And there are 576 Latin squares, but only 256 puzzles, so this gives us a different argument that there must be some puzzles with multiple solutions. But what about puzzles with no solutions? Maybe the only puzzles with no solutions came because I set those center entries wrong, like I intentionally set those entries or accidentally set those entries to things that they couldn't be. Maybe the only way I can get puzzles with no solutions is because of that. But the answer is no. If I look at puzzles like P0002, I can use my 2-cage lemma to show that these must be odd, these must be even. So I can't be odd and even at the same time, so this has no solutions. Similarly, P0012 has no solutions. P0022 has no solutions. P0013 has no solutions because these two would have to be odd, this would have to be even because these two have to add to 3. But these also have to add to 0 because that 2-cage would have a 0 clue once I fill that in. And there's one more I need to do with no solutions. That's a P0000 puzzle. That forces the center to be odd here. The Latin square condition forces the corners, and then there's no entries here that would give an even number. So there's a reason I did these 5 puzzles with no solutions. We're going to go back to those later as well. But now it's time for us to find our deductive process and show that this solution to this puzzle that Brian Hayes came up with is in fact unique. So what we're going to try and do is we're going to try to construct a parity map again, like we did before, in the 8 solution case.
Solution. Let's try everything.
All of this was first done in Python, and then yes, which is one of the reasons, yes. So Python did everything first before I got there. But these were the explanations that came later. Absolutely. Python was very good. So, making a parity map. Well, I know that this has to add to 2, so those have to be even. And I know that this has to add to 2 because of these outside clues, so these have to be even. Well, then I can get the other entry here. It has to, because of Latin square condition, I know those have to be odd, and these have to be odd. And I know that this plus this has to be 3, so that needs to be odd. And because there's an odd number there, that has to be odd. Now this forces the rest of the map. Those must be even, and I complete this as follows. But looking up here, these are 2 different evens, so they have to add to 2. So I know what this is. And now I can chase this 3 around the map. 3, 1, 3, 1, 3, 1, 3, 1. And then similarly, these 2 have to add to 3 because of the clues, so that's a 0, and I chase that around the map. So that's what I get. So notice that I didn't get to make any choices. This was completely determined by the entries, so we know the solution is unique. I didn't have to break it down into cases. I was able to get this solution directly from the parity map. So I've shown that the puzzle only has one solution. This was what the parity map looks like if I draw it like a graph. Notice there's something nice about this. The cycles cover the board, and both of these cycles contain entries in the center. So what I want to do is I want to make that into a lemma. Suppose every cycle in the parity graph of a puzzle contains something in the center. Then the puzzle must have at most one solution. Well, the thing is any one center vertex in this case is going to determine the entire puzzle. And there's only going to be 2 choices for that one entry. But that entry is going to make all the entries differ by 2. So it's going to make the 3 cages differ by 2 plus 2 plus 2. Which means they both can't be correct. So I have at most one solution whenever this happens. And we're going to return to that as well. Now, of course, this doesn't explain all the puzzles because there's plenty of parity graphs that don't meet the hypotheses of that parity graph lemma. But what have we seen so far? We've seen that there is a deductive method for solving this puzzle. The solution is indeed unique. The cage pattern in the Hayes puzzle is the only one that makes sense in this situation, and that we can change the clues to get puzzles with no solutions, as well as to get puzzles with multiple solutions. But what I'd like to do is I'd like to show that these are the only puzzles, or I'd like to classify the only puzzles with unique solutions. So that's going to be my goal. So in order to do that, I'm going to just need some a very small amount of group theory. It's going to all be done with the orbit stabilizer theorem. But what I'm going to do is I'm going to define PS to be the set of all puzzles, LS to be the set of Latin squares on my set. And if phi happens to be any bijection from Z4 to Z4, then we can allow it to act pointwise on both the puzzles and the squares. So it's going to map the clues A, B, C, D just by mapping each of the individual clues and each of the entries. And if this is a bijection, then it maps a Latin square to a Latin square. So if L happens to be any solution to a puzzle, and I have an automorphism of my group, then what I end up with is I end up getting a solution to the new puzzle when I map both over. And that's because if x, y, and z sum to C, then once I map them over, phi of x plus phi of y plus phi of z sums to phi of c. So basically what I get is for each automorphism of the group, I get a map that preserves the number of solutions and maps puzzles to puzzles. This is great news, but not so great news is in Z4 I only get two automorphisms. I have the identity and the map that negates everything. And this doesn't even reduce what we have to check by a factor of 2, because there's a bunch of puzzles that are fixed by this map. 0, 2, 2, 2 under the negation map just gets mapped to 0, 2, 2, 2. So this doesn't seem that good at all. But what I could also do is I can choose different maps. So what I can do is I can allow A to act on the puzzles by adding one to the clues, and on the Latin squares by subtracting one from the clues. And then I can use the fact that the clues happen to be in the 3 cages. So if I map over x, y, and z, which sum to some c in a puzzle, the x and the y and the z, well, they're each going to get subtracted 1, which gives me c plus 1, which is the clue of the new puzzle. So this is going to map solutions to solutions. Not only that, we can't generate any extra solutions as well, because this map is invertible, and otherwise we go back and forth and just ridiculous number of solutions, which can't be possible. So this actually preserves the number of solutions. So what we end up with is we end up with these two maps. Now I know that if I add 1 4 times, I get back to the identity, and if I negate twice, I get back to the identity. And if I negate, add, I get to the identity. So what we could do is we could extend this to an action of the dihedral group on the collection of all puzzles and squares. But you might be saying, well, isn't there a more obvious action of the dihedral group? And the answer is yes. We actually just let the dihedral group go by rotating and reflecting the puzzles. I'm going to let S be the reflection through the vertical line of symmetry in the center of the puzzle. And I'm going to define R to be rotation by 90 degrees. And now we have two different D4 actions that preserve the number of solutions. Now, even though the R and S don't commute with each other and the A and N don't commute with each other, it doesn't matter if I rotate and add, rotate, or if I add and reflect, or reflect and add. So the things in this D4 commute with the things in this D4. So we have a direct product of D4 and D4 acting on the puzzles and squares, which maps solutions to solutions and preserves the number of solutions. So from this we can now show that there's at least 32 puzzles with unique solutions. Well, we could look at everything that this group can map this puzzle onto, and each of those will have a unique solution as well. Now we can use negation to make sure that this entry is either one more or one less than the repeated clue. And then by adding, we can make that repeated clue anything I want. And then I can place the distinct clue in any of the 4 slots by rotating it how I want. So that gives me 4 choices for what I add to, and then 2 for whether I negate it or not, and then 4 for where I put the distinct entry, so 32 puzzles with unique solutions. But what I want to know is I want to make sure I get all the puzzles with unique solutions. Well, For this, all I need is the basics of the basic orbit stabilizer theorem. I'm going to define the orbit to be everything that the puzzle gets mapped to. The stabilizer is going to be all the group elements that fix that puzzle. And I know that the order of the group is the order of the stabilizer times the size of the orbit. For example, with our Hayes puzzle that he gave, we saw that there were 32 elements in the orbit, so that means the stabilizer was 2. And sure enough, this is fixed under the diagonal reflection. So that ends up being the stabilizer, as one example. But this action is going to partition my collection of puzzles into their different orbits. And it's not hard to compute either the stabilizer or the orbit in each of these cases. And we can compute whichever is easier in each of them in order to get the following table. So this sums up everything that's going on in this case. So I'll just explain how I organize this. This is one representative from each of the orbits, here on the left. I've organized them by the number of distinct clues. So this is one clue, 2 different clues, 3 different clues, and all 4 possible clues. This is the stabilizer. This is the order of the stabilizer. This is the size of the orbit. And notice that I started to fill in the number of solutions with what I did before. The reason I chose those 5 examples of puzzles with no solutions is I wanted to fill in these entries, and those are actually all from distinct orbits. We know that there's 32 in this orbit here, and we got this from my 8 solution puzzles as well. So I've actually summed up everything but these 6 already in this situation. Oh, and one more thing. Every puzzle has to fall into one of these categories. So this column has to add to 256. But not only that, every Latin square can be used to generate a puzzle. So, and the number of solutions is going to be equal to the number of Latin squares that generates that puzzle. So if I take the entries in this column and I multiply them times the entries in this column and add them all up, I have to get 576, which is the total number of Latin squares. So this gives us an equation that we can use. So we basically have those 6 unknowns. What I could do is I could define x of p, a, b, c, d to be the number of solutions to that puzzle. And it gives me the following equation, with minus the 64 for the ones we already know with our solutions. And if this had one solution, we'd be done, but obviously this has many solutions. But if I only want to classify the puzzles with unique solutions, all I have to show is that each of those things happens to be greater than 1. Each of those variables is greater than 1. So there's a number of ways I can do this. And what I'm going to do is I'm going to choose one puzzle from each orbit together with a group element that fixes that puzzle, but doesn't fix the solution. And I'm going to exhibit one solution from each of the puzzles. So in this one table now, like for example over here, this is a puzzle representative from one of the orbits, 0011. If I reflect over a vertical line of symmetry, I'm going to switch these 2 entries and these 2 entries, so this puzzle's fixed. But this solution, in fact, no Latin square is fixed over this vertical reflection here. These 3 puzzles are fixed for sort of reflecting over a diagonal line of symmetry, the group element RS. And of course, you can see none of these puzzles, this one would map the 0 onto the 3 onto the 0. None of these puzzles are fixed under these elements. So these all have to have multiple solutions. Here, if I add then rotate, you can see this goes to itself, but this doesn't. And here, if I add twice and then switch these 2 entries, this puzzle's fixed. And you can see this solution is not fixed under this element. So what this does do is it allows me to fill in that each of these has to be greater than or equal to 2, thus showing that the only puzzles with unique solutions are those 32. And another way I can describe that is a puzzle has a unique solution if and only if 3 clues are equal and the other clue happens to be of different parity. Okay, but we're close to proving everything. So I want to complete that table totally. And one way we can do that is to try to find tight upper bounds. So if we can get the right upper bounds for each of these, then the only way they can add up to 512 is if they're at their limit. So what I'm going to do is I'm going to just look quickly at some of these cases. Now, for the P0011 case here, there's only going to be 2 ways we can complete this parity map. And these both satisfy the hypotheses of the parity graph lemma, which means they can each have at most one solution. Those are the parity graphs. So you can see they meet the hypotheses.